Welcome and thank you for joining us today. I'm Jennifer Matthews and I'll be your moderator for this Masters of Reliability webinar on separable connectors, common failures, and how to avoid them. The content of today's webinar builds upon our mission to extend craftsmanship mastery to circuit owners and their contractors to improve reliability. For those of you new to the Masters of Reliability webinar series, links to recordings of past webinars may be found online at the link provided on the screen. While you're there, please also be sure to sign up for Mike Sapolli's P1816 implementation webinar on November 2nd. Joining us today as our expert guest speaker is Glenn Lutze of Richards Manufacturing Company. He began his 40-year career in power engineering with the Okanite Company as a research engineer in the high voltage laboratory. At Elastomold, he was promoted to Director of Engineering, where he headed the design and development efforts for joints and separable connectors. He later joined Richards Manufacturing Company as the manager of the medium voltage product line. Glenn has authored 20 U.S. patents and serves as chairman of the committee responsible for revisions to the IEEE 404. And with that, I'd like to turn the presentation over to Glenn.
Thank you, Jennifer. Before we begin, I'd like to extend a thank you to Glenn Bertini for having the vision to recognize the value of something of this webinar series to our industry, and also thank Jennifer for all your untired help in putting today's session together. Here is the agenda that we're going to be going through today. We're going to start with a definition of separable connectors and look at the specific types that are available today. We're going to look at the industry specifications that govern separable connectors. And then we're going to get into the failure mechanisms. And what I've done here is I've broken these into failure mechanisms that are related to the current carrying portions of the connectors, and then those that are related only to the voltage or the dielectric portion. Now, you have to remember that most current-related mechanisms may start as a heating problem, but the only way you find them, they only manifest themselves to an engineer is when they become a dielectric failure and they trip the breaker out. And then we're going to wrap up, and at that point we're going to take questions after the wrap-up. Now, Jennifer has told me that you can put your questions in as we go along. I urge you to do that, and she will keep track of them. This way none of them are forgotten. With that, we'll get started here. Hopefully when we're done today, you will be able to understand the three classes of separable connectors that are currently in the IEEE 386 standard. That's the 2006 version of IEEE 386. Now there is a fourth class, that's why I mentioned 4 classes up here. In the next revision of IEEE 386, we expect to have another class of separable connector, which we're going to go through today. We're going to go through the standards that govern not only the geometry, but also the ratings and the qualification requirements of separable connectors. And then we're going to go through current and voltage-related failure mechanisms so you can understand the differences between them, and then recognize the root causes of either one of them. And when we have all that together, this will give you a much better understanding of how we can improve the reliability of the connectors, of separable connectors, and ultimately the system. So let's start with the definition of a separable connector. This is the definition as you see it in IEEE 386 today. There's only 2 areas that I want to key in on here, and those are the 2 areas that differentiate a separable connector from other connectors like a live front termination. And the first section is the fact that a separable connector is fully insulated and fully shielded. Obviously a termination is not shielded. The second area in this definition that differentiates these connectors is the fact that the connection can be easily or readily established or broken. What we mean by that is if you have a low break elbow, you're on the end of a hot stick, you can engage the elbow to the insert and complete the connection. So you're establishing the electrical connection, or you can remove the elbow and break the connection. So the separable connector types, the first type that I'm mentioning here is the 200 amp load break, and that's because most people are most familiar with this. But the reality is the 200 amp dead break system was really the first, the forerunner of all separable connectors. And the differences between the two of these, one you can make and break under load on the left side, the load break one, and the dead break one, the circuit has to be completely de-energized. Since these two systems are very, very similar, I'm going to treat them going forward as one group. The last group that's in the current standard, the 2006 version of IEEE 386, is the 600 amp dead break system. And this is either, people call them T-bodies or hammerheads or 600 amp elbows. That's what 386 looks like today. Hopefully in a few years, by the way, Tim Wall is the chairman of the committee that that is looking at the revisions, the next revisions to IEEE 386. And so he will be responsible for putting some of the things that we're going to be talking about into the next revision. The disconnectable I's, Y's, and H joints here. Now the first question that may come to mind, you see the word joint. People call them joints or splices. The first question is why are these going to be put under IEEE 386? Both Tim Wall's group, the Separable Connector group, and my group, which was the standard for joints, both groups decided that because of some of the similarities, they were best suited to go into 386. In particular, there is a lug that gets bolted in here. It happens to be exactly the same lug that you'll find in the 600 amp dead break system. Also, if you look at the back end of the 600 amp dead break elbow, it's exactly the same as the back end of the disconnectable splices, and they both accept the same cable adapter. Now we're going to be talking about cable adapters going forward, and currently the standard does not have any geometry related to that, but the next revision of 386 is actually going to call out the geometry of the cable adapter. So those are two similarities. And then finally, this T-body, the 600 amp dead break elbow, there are many accessories associated with all of these connectors. But there's one accessory in particular, what we call a connecting plug, where you can stack two dead break elbows together, and that's a joint or splice configuration. So there is a precedence to say why this joint should be in 386. Now let's look at these in a bit more detail. The 200 amp load break or dead break system consists of an elbow housing, an insert, and a well, a bushing well. The 600 amp dead break or T-bodies consist of, again, an elbow housing, and here you can see the cable adapter, which I don't call out in this particular screen. We have the apparatus bushing, and finally an epoxy insulating plug and cap to close the whole connection together. By the way, we call it an elbow, even though the shape is far from an elbow shape, but since the 200 amp load break and dead break elbows were the first systems, that name sort of hung around elbow. The disconnectable joints, again, these are not in the current standard, but they are almost definitely going to be in the next revision. They consist of a splice body or a yoke and a sleeve or receptacle. Now let's look at the industry specifications. We've been talking about IEEE 386. The actual title of this standard is the standard for separable insulated connector systems for power distribution systems above 600 volts. The first change that may occur in 386 is in the title, and that's only because the word above 600 volts isn't really definitive. The standard only goes up to 35 kV, even though that's usually the maximum distribution voltage. This may be changed. That's yet to be seen. Within IEEE 386, there is a few standards. One of them is IEEE 592, and the title of that standard is the standard for exposed semiconducting shields on high voltage cable joints and separable connectors. Now, as we mentioned in one of the first slides early on, that the outside surface of these connectors are fully shielded. They are fully shielded, but they are shielded with a semiconducting rubber. Now, the value of IEEE 592 is it specifies what that semiconducting shield must do. Obviously, when an elbow is sitting out in the field energized and someone enters a manhole where one of these connectors is, and they accidentally touch the connector, we certainly don't want anybody getting hurt. So one of the requirements of 592 specifies what the insulation resistance has to be from end to end of that connector. The other portion of IEEE 592, many people know it as the nail test. This is the area where, imagine a separable connector in the field, and it somehow the dielectric punctures, it fails. We want to make sure that when it punctures, that the semiconducting shield is capable of carrying the fault current to remove the breaker out of service to drop the load so no one gets hurt again. And in reality, 592 requires that to happen 2 consecutive times. We're not going to get into that why at this point. Okay, another standard within IEEE 3D6 that governs these connectors is ANSI C119.4. I think everyone recognizes this standard. Again, this standard has just undergone a major revision. Up until the last revision, this standard was for connectors that were used between aluminum cables, aluminum to aluminum, or an aluminum to a copper cable. This current revision now has performance criteria for a connector that's used on a copper-to-copper system. So, just a quick poll, something for people to think about while we're going through this, is most medium voltage connectors share common failure modes? Yes or no? And this is all the different connectors, the 200 amp load break, the 200 amp dead break, and the disconnectable splices, and the 600 amp T-bodies. Do they all share common failure modes? So now let's start.
Just a second here before we move on. Let people have a chance to answer.
Okay.
3 more seconds. All right, I'm closing the poll now. And there's a quick share of what everybody replied with.
Okay.
All right, and then...
okay, I'm not sure I see the results here, but let's go on and we can all think about it for those who haven't answered. We're going to look at, again, I've broken the failure mechanisms into 2 groups. The first group, we're going to look at just those mechanisms that start as a current-related mechanism. So again, let's look at the 200 amp load break and dead break connectors. We've identified the elbow housing just so that you can get your idea of where this picture is. We have the housing, we have the insert, we have the bush and well. Since we're talking about current-related phenomena, the more important things are what's on the inside. On the inside, we have a probe, the elbow probe, and that, when we're talking about load break connectors, this always has a tip, a plastic white tip. That tip is an arc quenching tip. What the purpose of that is, in case someone might be new to this whole line of connectors, as you start to remove this elbow off an energized circuit, again, we're talking strictly the load break elbows. As you start to remove it, you're going to develop, once the metallic probe breaks the connection with the insert, we're going to develop an arc there. That arc, at that point, this arc quenching tip is going to be right in the area where the arc is. That arc is going to play on the surface of the arc quenching tip. It's going to ablate the surface or melt it. When it ablates, it's giving off a gas which tends to quench the arc by increasing the dielectric strength of the air in there, so thereby reducing the arcing time. So the other part of the connector system that we're going to be looking at is the connector itself. So what do we have to worry about? Bill Taylor, in his first presentation, in the first presentation in this web series, talked about cable preparation in depth. There's a few things I think that we should go through them. Just it's worth saying over and over again. Again, we're talking about cable preparation only in the area right now. We're limiting it to exposing the strands of the conductor. So you're cutting through the insulation and removing that insulation off the end. The first thing we have to make sure is we don't cut any strands. It's obvious that if we cut a strand, let's take a number 2 cable. It's a number 2. It only has 7 strands. If we were to cut one of those strands, and we're carrying full current, we're carrying 200 amps, now we only have 6 strands left to carry that 200 amps. And also 6 strands left to carry 3,500 amps for 3 seconds or 10,000 amps for 10 cycles. Those are all currents that have to be carried by those remaining strands. Now, it's not hard to imagine that with less strands carrying current, we're going to get a localized hotspot here. What happens is that heat that is generated in this area is going to start degrading the insulation, the dielectric of the housing, and eventually we are going to end up with a voltage-related failure. We're going to end up with a puncture right out the side of the housing, somewhere in this area. But again, it began as a current-related phenomenon. Now, another problem is nicking the conductor. You might say, well, that's not so bad. If we nick it, it's still going to carry most of the current. That is true, except for one thing. If you put a small nick in an aluminum conductor cable, and there's any mechanical force, and there will be, as the cable heats up, expands, and contracts, if there's any through faults, there's going to be movement in that area. Eventually, where that nick is, the strand will break, and we're going to end up with exactly what we had here, a cut strand, the same issue. We're going to end up with a dielectric puncture in this area. Now, another area, the next 2 items are really tied together, the number of crimps and the proper dies and tools. By far, this is the most critical area of the current carrying portions of the connector. The dies are fairly straightforward, the dies and the tools. These are the ones that the splicer has on his truck. What he doesn't have is the number of crimps. This is something that every manufacturer supplies with the connector. Now, let's go back a few years when cables were strictly stranded. There was no strand filling. If you put 2 crimps on a connector, and we were carrying, instead of 200 amps, we were only carrying 30 amps or 40 amps, which is the normal current for most of these connectors for most of their life. 2 crimps probably would have carried the current. It may even have carried the 200 amps for a while. The problem is today, the growing strand fill cable usage is growing a lot. 2 crimps will not work. If the recommendations by the manufacturer say that if you're using a BG nose die, you should put 5 crimps on, and you only put 3 crimps on, eventually that connection is going to overheat, and we're going to have a dielectric puncture. So that's probably the most critical area that we're going to talk about. One other area, we've got the cable prepared now, and we're going to put it into the connector. It's very important to seat the conductor all the way to the bottom. If you put the first crimp on right at the crimp line, which is up here somewhere, and the conductor is short, it's not underneath the die, you might as well assume that you didn't put that particular crimp on. So you're back to the same issue as having too few crimps. Now, another area is the probe to the connector where that connection is made. We have to make sure we have the proper torque. The good news is that every elbow goes out. Every manufacturer supplies a wrench, a throwaway wrench with every elbow. It's a probe wrench. There's usually a hole right in the probe about over here. The wrench goes into the hole. All the splicer has to do is tighten this connection up, thread this in, and tighten it until that wrench bends. If the wrench bends, he knows he has the proper torque. And also the 200 amp dead brake connectors also have a throwaway wrench similar to that. Now, there are tools on the market that have built-in torque limiters on them. That's also another way to do it. Another area of the current carrying portion is this insert and well stud threaded connection. This well has a 3A16 copper thread here. That copper stud has an ultimate breaking torque of about 20 foot-pounds. And in fact, IEEE 386 has a performance criteria that a manufacturer has to take 4 parts and has to be able to show that it will hold 17 foot-pounds. What happens is when an installer is putting the insert into the well, he greases everything up properly, he's threading it in. It is not difficult when you're gripping the outside surface of the insert to exceed 20 foot-pounds and break that stud off. That's certainly bad news initially, but the news gets worse because now you've got a splicer who knows he was twisting and he broke the stud. You can be sure that every subsequent part that he puts together, he is going to remember that he broke the stud and that he has to be careful. Now, instead of the accepted 12 to 15 foot-pounds of torque, he may only have 5 to 8 foot-pounds. So that is a problem area. Okay, for the 600 amp dead brake connectors, we have identified the cable adapter I mentioned to you, the elbow housing, and the insulating plug and cap. Again, we're looking at current-related phenomena, so let's see what's on the inside here. Oh, I forgot, we also looked at the bushing, so we have that part there. So on the inside, we have a connector, and we have a stud. Areas that we have to be concerned about, cable preparation again. Exactly the same issues that we looked at on the 200 amp line. Obviously, a nick on a 61 strand conductor isn't as critical, but we want to make sure we don't do that. Another area that's sort of unique to the 600 amp dead brake system is this area. The top of this lug usually has a through hole up here. That through hole accepts this stud. What happens often is a splicer prepares the cable, puts the cable adapter on, puts his connector on, pushes the elbow housing on, lines up the hole. Now he greases the 600 amp bushing, and now he starts to move the elbow housing over to put on to the bushing. And it's just a little bit short. The cable's just a little bit short. So he lifts up on the elbow, figuring that he's lifting everything up. Unfortunately, what happens is the elbow slides off the cable adapter, and the hole only has to slide down 5/8 of an inch, and he puts the insulating plug through with the stud, and he misses the hole. What happens is he ends up pinching the top of the connector right here. He torques it, everything seems good, and everything is good for a while. It will carry current, but what happens as soon as he starts getting any mechanical movement, again through thermal cycling, through faults, anything else, it will work its way out and eventually fail. The threaded connection that uses the stud. The first area that is of primary concern is the stud. 386 right now calls out 2 different lengths of stud. One stud length, the shorter one, is for the 15 and 25 kV class elbows, and there is a slightly longer stud for the 35 kV class connectors. Now, if your utility happens to use both 35 kV class and 15 kV class connectors, and the studs are loose, somehow or other, we often see failures occur because a 35 kV stud, the longer one, gets put into the 25 kV application or 15 kV application. It's a little bit longer. It bottoms out in the hole. The splicer torques everything together. He gets his 60 foot-pounds. He thinks he's tight, but in reality, he doesn't have contact between the faces here. So that's the first issue. Also, there are several specialty studs in some specialty connectors out in the field. These studs are not even the same length on each side. If they're used in a non-special application, and they're put in the wrong direction, they will bottom out on one side of the hole, and again, the torquing will not allow the two faces to come together. It's absolutely paramount that the faces of the lug and the bushing mate. The second area of concern is the torque, and everybody knows 50 to 60 foot-pounds. The reality of this connection is if you were to torque this to get only 10 foot-pounds, it will actually carry 600 amps, no problem. It will carry 600 amps forever. It may also carry 25 Ka with not an issue. That's the high through fault rating for this connector. The problem with it, if this connection is tightened to 10 foot-pounds and we have a through fault, let's say we have a 25 Ka through fault, that through fault is going to move the elbow. It's actually going to twist it about the stud. If that elbow twists in a counterclockwise direction, the way the stud grips the inside, it will actually loosen up. And then when the elbow goes back in the clockwise direction, unfortunately, it doesn't retighten. So you start with 10 foot-pounds, and after the first movement of that connection, you only have zero, you're down to zero. It no longer will carry 600 amps. And another interesting fact about this type of connection, if the elbow happened to move in the clockwise direction, that's in the direction of tightening the torque. So if you start with 10 foot-pounds, you would think, oh, well, I'm going to get tighter. What happens is when the elbow, it doesn't get tighter, first of all, and then when the elbow goes back to the neutral position, it moves in a counterclockwise direction. That will loosen up the stud also. So an area of concern. If the requirement is 50 to 60 foot-pounds, make sure you've got 50 to 60 foot-pounds. Looking at the 600 amp disconnect splices, we've identified the yoke and the sleeves or the receptacle. Now looking on the inside, we have the connector, and again, as I mentioned, this is exactly the same connector that we just discussed. Exactly the same dimensions, everything about it is the same. We also have the bus yoke, or the conductor of the bus. And finally, the fastener. Those are the three areas that we're going to be looking at here. Cable preparation, there's no sense even going through that again. The fastener itself, the proper torque. It's essential that we have the proper torque here for exactly the same reason. If you tighten up to 5 foot-pounds and there's any kind of mechanical movement, that connection is going to loosen up. Now, in the industry, there are some specialty bolts that take this completely out of the equation. There's a shear bolt head on top of this other bolt where when you torque it, you shear the head off, you know you've got the proper torque. And if you don't have the proper torque, if you don't shear the head off, you can't get the sleeve on. So it's a fail-safe system that is available in the market. Now let's look at some specific failures relating to torque, or I'm sorry, to the current portions of the system. What you're looking at here is a T-body, 600 amp T-body. You've got a lug, you've got the insulating plug, and you can see the severe melting of the end of the lug in this area here. Now, when you first look at this picture, I'm sure the first thing everybody keyed on was the fact that we are looking at 1/3 of this lug and we don't see any crimps, which means the first crimp is way down. Even if they started down here and all the crimps were put on right next to each other, there's no way that they would be able to get the proper number on. But again, when we looked at this, we would have expected a failure out the side of the housing down here. So where the hole was actually right up here, and it's in the half of the elbow that you can't see. The failure is looking right at your eyes now. That's where the hole was. And the way we finally determined that there was insufficient torque was we looked at this surface on the back side. It looks a little distorted here, but it was actually straight. And we saw black marks around the entire surface. There should have been a circle 1 1/4 inches in diameter, which represented the bus bar in the bushing. You're going to see this a little bit later. It's much clearer in a different picture and a different phenomena. Another current-related phenomena. And again, insufficient crimps like we talked about. This is a copper conductor cable. The lug here is copper. This connector in the next revision of IEEE 386 is going to be considered a 900 amp connection. With 3 crimps, there is no way that this connector could have carried 900 amps. Now, we know it was torqued together properly. Remember I mentioned that there should be a mark? You can just see the surface of the lug here. That outline is exactly 1 1/4 inches in diameter, and that's where the bushing contact or the insulating plug contact moved around the surface and smoothed it off. We saw this impression on both sides, so we know the torque was proper over here. So the heating was occurring over here, and right where you would expect it, this is the hottest portion of the connector between the end of the insulation and cable adapter and the end of the lug. That's the hottest part. It damaged the insulation in that area, and we had a failure, a puncture of the dielectric right in that area. Now, let's move on to voltage-related phenomena. When we talk voltage, the first thing everyone thinks about is electrical stress analysis. And this is a typical stress plot. What we have here is we have the cable conductor. By the way, these are the ones I'm going to be showing are axisymmetric. The line at the bottom of the white circle is the very center of the conductor. So what you're looking at here is 1/2 the diameter of the cable conductor. Then we have the cable insulation. Here we have the accessory jacket, and this particular accessory is either a 600 amp T-body or a disconnectable splice. And we know that because of, well, you'll see in a moment, the cable adapter. This is the conductive insert of the T-body, and this is the insulation. Here, this section here is the cable adapter insulation and the cable adapter stress cone. So we have this stress plot. What do we do with it? Here's how a manufacturer uses a stress plot and stress analysis. Before we run the stress plot, it's essential that we determine or have a good idea of what stress our materials are able to withstand on a continuous basis. This is the bulk insulation. All this area, the cable adapter, this is all bulk insulation here. What stress are we going to allow here? Now, let's say for the sake of argument that this connector, we want to have no more than 120 volts per mil. By the way, I think better in volts per mil. It's difficult for me to think in kV per millimeter, so I will only be talking in volts per mil. We're saying that we have a requirement that anywhere in this bulk insulation we cannot exceed 120 volts per mil. That's not the end of it. We have 2 interfaces. Every separable connector has at least 1 interface. The interface between the elbow housing and the underlying material. In this case, it's a cable adapter. If it happened to be a low break elbow, this would be cable insulation. So we have to identify what stress we want to allow here. And in a T-body, we have 2 interfaces. We also have this interface between the cable adapter insulation and the cable insulation. So let's say for the sake of argument that we allow a maximum of 40 volts per mil anywhere along any of these interfaces. So we run the stress plot. These lines that you're looking at here, and there happens to be 30 of them, each one of these represents a point of a constant voltage. So if you follow this around, the voltage at any one of these points is exactly the same. And since there's 30 of them, let's say for the sake of argument that we're going to put that this is a 25 kV elbow. A 25 kV T-body only has a single phase rating, which means the most it can have across it is 15.2 kV line to ground. So on our cable conductor, we're going to put 15 kV, and on our jacket and shields, we're going to have 0. So if we have 15.2 kV, we know that the voltage difference, the delta from one line to the next, is we have 30 lines here. 15 kV or 15.2 kV, we have about 500 volts from line to line. So if we know the distance between the lines, it's simply 500 volts divided by that distance. For the most part, you have to make sure you resolve that vector into its two components. The vectors are normally given perpendicular to the stress line. So let's look at another stress plot. This is an improper cable preparation. On the right side, we have proper installation. This is exactly the stress plot we just looked at. And again, since both plots are actually symmetric, it almost looks like a complete part here. But the left side is where we're going to look at the difference. So let's look at the elements that we just identified. Again, we have the cable conductor, and that's the cable conductor on both sides for the proper installation or the improper installation. We have the cable insulation. We have the accessory jacket, the conductive insert, the insulation system of the accessory, the cable adapter insulation, and the cable adapter stress code. So you look at that plot and everything doesn't look too bad, but let's key in one particular area. On the right side, I'm calling this a proper installation. On the left side, we have a problem. Well, what is the problem? On the right side, the cable adapter, this is the cable adapter, it ends way up here, right flush with the cable insulation. Both of these dielectrics are terminated well inside the conductive insert. On the improper installation, you can see the cable insulation and the end of the cable adapter are both short of the conductive insert. So you say, well, so what's the problem? If you look at the stress lines, the equal potential lines here, they don't look a lot different. Yeah, they're bending a little bit more up here. So what is the problem? Let's look at it a little deeper. This area right in here, we said we have 40 volts per mil along the interface. Perpendicular stress may be 50 volts per mil. Now, 50 volts per mil in EPDM is well within the operating voltage of that material, certainly within the operating voltage of cable insulation. On this side, you can see that that stress line is bending a little bit more. When you do the analysis, it may end up that we've increased the stress. Instead of 50 volts per mil, now we've got 55 volts per mil. Again, you might be saying, so what's the big deal? The problem here is this cavity, which should have cable adapter insulation and cable insulation, has air instead. What's the dielectric strength of air? For a cavity this size, we usually use a number like 45 volts per mil, maybe 50 volts per mil. So what's happening here? We said we have 55 volts per mil in this area. Now you can see the problem. The air can't hold off that dielectric strength. It's going to start buzzing, partial discharge. That partial discharge is going to start eroding the insulation in this area. It's going to erode it continuously until eventually we have a puncture out the side here. Now let's look at some specifics with the connectors. Again, we're lumping the dead brake and the load brake connectors together. Here's the 200 amp. We've identified the wells, so you can see them again. We've identified the housing, the insert, and the well. Inside, we've identified the connector, the probe. Now, let's look at areas that we have to be concerned about. Cable preparation. Before we talked about cable preparation, we were keying on cable preparation as it related to the area of the conductor. Now we're looking at cable preparation on the insulation surface. The first most important thing, not most important, but an important thing, is that the cutback is correct. You can see here, down here in the lower portion of this slide, this is the insulation shield, the semicon. The semicon is short. It should be inside the housing here. We all know that if you see insulation here, there's a potential problem. So cutbacks are critical. Now let's say we've got the proper cutbacks. The next issue is we have to look at the surface and make sure we don't have any knife cuts or gouges. Let's say we do have a knife cut. What do you tell your splicers? Certainly, if it's a deep knife cut or a deep gouge, they have to re-terminate the cable. Hopefully they've got enough free length of cable to re-terminate. If they don't, what they usually will do is try to sand out the knife cut with sandpaper. And that's okay if they do a smooth job and they don't leave a flat on the end of the insulation. Now we've got a nice smooth surface. Everything looks good. The next thing we have to do is make sure we have no contamination. The contamination on the insulation surface usually comes as a result of residual pieces of semicon, microscopic, they're very small, actual carbon particles that are embedded on the surface of the insulation. How do we remove those? Some utilities allow their splicers to go in there with, again, fine sandpaper and remove the contamination that way. The better way to do it is to use a solvent, soak a rag with solvent. It's important when we do this that we wipe from the inside, we wipe toward the cable. Always wipe in this direction. Why do we do that? If you wipe with a solvent in this direction from the cable shield down the insulation, we're going to drag carbon particles from the insulation shield here, and we're going to drag it down the surface of the insulation and contaminate things even worse. So now let's assume we've got no contamination, everything's clean, ready to go. The next thing is we have to make sure that we grease things properly. Now we're going to talk about greasing the housing also, but you're going to see in a minute that it's difficult to do that, so it's very important that we grease the cable properly. Now greasing does a lot of things. It certainly makes it easier to slide the housing on, but grease also fills in microscopic defects or areas where air can get trapped. In particular, that grease is going to build up on the right in this area where the semicon terminates, and it's going to get put, as you're sliding the housing on, it's going to push the air out of that area. So it makes a much better connection. So we want to make sure that that cable is thoroughly and properly greased. Let's look at the housing. The first problem with the housing, we have to make sure it's properly sized. Well, that sounds easy at the first blush. The dimensions are right on the housing, usually engraved near the bottom somewhere, and it tells you what the minimum, usually you're only concerned about the minimum number on that elbow housing. The reason being that the top number, if you try to exceed that, it just gets too difficult to put the part together, and your splicers are going to complain about it. So we're only concerned about the minimum number. What does that number mean? It tells you the minimum diameter of this insulation across here that this housing will work properly on. So that sounds pretty straightforward. You go to the cable manufacturer and you say, I've got number 2, 100% insulation. What's my diameter? What's the diameter of my insulation? You get a number. The problem is that's not the minimum number that can be. Both AEIC specifications and ICEA specifications allow that nominal number in cable insulation diameters to vary. You have to know what is the minimum that can be. Are you done at that point? No. Unfortunately, going back to cable preparation, if there was a knife cut on the insulation and the splicer sanded the knife cut out, did he reduce the diameter of the insulation? If he did, you have to take that into account. When we are cutting the insulation shield back, there are tools on the market that make this much easier. Some of those tools actually remove a portion of the insulation. Not a lot, but it does remove some insulation. What does that do? It reduces the diameter of this cable even more. So the size that's on here, that minimum size, is the diameter of this cable just before you're ready to slide the housing on, taking all that into account. So now we've got the proper housing. We've got the proper cable all ready to go. We have to make sure that the housing is greased. Again, the hole is very small. It's not as critical in this area down here. If you can, most splicers do put some grease up in there, but you can't get up in there. We rely on the cable being properly greased over here for the most part. When we slide the housing on, we want to make sure it's positioned properly. By proper, we want to make sure that the lug is fully up to the top here. When that's fully up to the top, it allows the connection to be made to the probe. Now, if the housing is not properly positioned, you're not going to be able to get the lug in, the probe in. But you want to also make sure that those probes, the threads are aligned straight out so we don't do any cross-threading. Now, the more critical area for greasing is in these two interfaces. And by far the worst area is this, the operating interface. But for the minute, let's just look at the two of these together. We want to make sure that we use the proper grease. Now, these materials that are used to make almost all these separable connectors is EPDM. It's an oil-based rubber. If we happen to use, say, Vaseline to lubricate this surface, there is no doubt that it would lubricate it. You'd be able to put the elbow together and it would work fine. The problem with Vaseline, because it's oil-based, it will absorb into the rubber here. First thing it's going to do, it's going to swell the rubber. If there's not a lot on there, it may not swell it too much, but what happens is if you come back in 3 months and try to remove this elbow, you're not going to be able to remove it. So grease type. The grease that's recommended is a silicone-based grease. The amount of grease that we use. Now let me go back to grease type. One other issue with grease, and I hear this very often. I've got two greases out here. You know, I've got one that's nice and thin. It goes on so smooth. I can wipe it so easily on here. Very easy to thoroughly grease this interface. And you know what? It works fine. It works great. Except if you go to remove this elbow in 3 months, you will not be able to get it off. What happens with the grease when it's put on in here is the pressure of the interface that's built into it pushes on the silicone grease. The silicone grease migrates out this way. It migrates out this way. There was a Yukon study done years ago where they actually found silicone grease, I believe it was 15 inches down the conductor of the cable. That's how far it migrates. Silicone grease does not migrate into the insulation. It's a misconception. People think of the interface drying out, that because the grease got absorbed in. It does not absorb in. Got to use the proper grease. The heavier grease stays in place. The amount of grease. We've got the right grease. Can we over-grease it? Yes. This interface, if you put too much grease on here, well, there's only a very small reservoir down here at the bottom. If you put too much on, you're not going to be able to get this insert on proper. If you put too much, and it takes a lot of extra grease, but if you put too much on here, you're going to get it down in this area. You're not going to get the elbow seated properly. The bigger problem is using too little grease. And that comes down to whether it's uniformly distributed and uniformly applied. And again, this interface, the operating interface, the interface that you're going to rely on to be able to be operable for the next 40 years, you want to be able to remove it and put it back on. Let's take the extremes. Let's assume that your splicer puts absolutely no grease on. He pushes the elbow on. He's a big burly guy. He can get it on, and he will. He certainly won't ever get it off again. That's the first problem. But the second problem is, as he puts it on, this rubber against rubber starts to produce microscopic ripples, just like pushing a rubberized rug across the floor. It starts to buckle. You can't see it, but embedded in that buckled area is minute amount of air. We've already talked about air. it has a lower dielectric strength than the rubber, you can't have that. Just because you apply the grease to 90% of the surface, if you don't apply it to 100% all around, even on the bottom where you can't see it, you're not doing a good job of uniformly applying the grease. After you've got everything all mated up, the final thing that you have to make sure is that all components have to be grounded. There are eyelets in the elbow. There are eyelets in the insert. 600 amp connectors all have eyelets. We're going to go through those. Make sure they get tied to ground. So, in the 600 amp dead break connectors, we've identified the housing, the bushing, and the epoxy plug, and the cable adapter. Cable preparation, there's no sense in going through that again. Exactly the same thing as we just talked about. The cable adapter, we've talked about this also. Cable adapters have a sizing just like the elbows. You got to make sure it's sized properly, greased properly, positioned properly. Once you've got the cable adapter in place, the housing is the next thing. The good news, there's only one housing. A 1525 kV housing fits on a 1525 kV cable adapter. 35 kV housing only fits on a 35 kV cable adapter. So that's an easy one. But again, we have to make sure it's properly greased. The epoxy plug and the bushing, two more interfaces, we want to make sure that they're properly greased. And finally, everything is done. We want to make sure that at least a ground is put in at least one of the grounding eyes. Some elbows have grounding eyes up here in the corner. Some have them down here by the cable adapter. Some have grounding eyes in both locations. One of these has to have a ground wire to ground. The disconnectable splices. Cable preparation, no need to go through that again. The cable adapter, exactly the same as before. The bus, greasing it properly. The receptacle, no surprises there. And finally, we have to make sure we've got grounds in each of the components. In this particular configuration, this is a Y configuration, so there's 3 sleeves. We should have a ground on each one of the sleeves and also on the yoke. So, what does an electrical issue look like? Well, here's a piece of cable. There's the cable insulation you can easily see. Here's the cable lug, and this came out of a T-body. You can see the knife cuts all along the surface here. And those knife cuts caused what we call an electrical creep down through the knife cuts, and the fault current came over here and eroded the surface. Contamination. Here we have a cable adapter, and this is the end of the elbow housing. You can see it cut away, and you can see the erosion in this area here. Now, this is the way the part came back to us from the field. I urge you, when you're cutting these parts in the field, you can see this knife mark. That knife mark in the surface of the cable adapter was obviously made when the housing was cut off, but sometimes the person who looks at this last may not have the housing, and people say, well, what caused the failure? Well, you start looking at things like this, and you start to wonder whether that caused the problem. The other thing is, normally you would make your cuts away from the area that was eroded. So, one more. This is a T-body, if you can see it. This is the cable entrance down here. Here's the area where the bushing would go in. And you see all this erosion here. Now, this part did not fail in the field. It was removed because a splicer went into a manhole, heard this elbow buzzing, and said there's a problem. He notified his supervisor. They eventually took the circuit out of commission, took the breaker out, removed the elbow, sent it back for analysis. What we did back here at Richards, we cleaned it all up, put it back on our production test. Everything passed production test, no problem. And then looking into it, there are 4 grounding eyes on this elbow, and not one of them was pierced. So we knew absolutely, although we were pretty sure before that, that there was no ground. So what happens? As the sine wave voltage builds up, you build up a charge on the outside here, and it's going to discharge to the closest ground. In this case, it was the faceplate of the network transformer. It started arcing to it. This, I just threw this slide in. It's not an electrical problem. It's not a current-related problem. It's a mechanical problem. I mean, it certainly could have ended up in a voltage-related problem, but this is a spanner wrench, misuse of a spanner wrench. Epoxy parts on the 600 amp connector line they have holes, usually 3 holes around the circumference. And a special wrench, a spanner wrench, goes into the hole. You put a torque wrench on the spanner wrench, very awkward to do, but that's the way it has to be done, and then you tighten it. What happens is, the first time someone uses a spanner wrench, invariably they put it in the wrong direction. And then you try to torque, and what happens is it just rips out a section of epoxy. The other problem that happens is by the time you've put the spanner wrench into the hole and you put the torque wrench on it and you're all ready to, and the torque wrench is awkward because you might be hitting something and the spanner wrench slips out of the hole a little bit, and then you put the torque on, you crack the epoxy. So let's have our wrap up. I guess we went through our polling over there. Let's see how we did. The key points, hopefully, that I've hit on is that medium voltage accessories, whether they're 200 amp load break, dead break, T-bodies, separable joints, they all have, many of them have common failure modes. And those failure modes have common causes. I hope everybody got that right. The predominant failure causes, such as too few crimps, are easily discoverable. They're understood. Once we define them and we understand them, if we pass that knowledge along to the installer, we can certainly improve the reliability of the accessories and ultimately the reliability of the system. So thank you very much for your attention, and I hope you got the answer to the question over there. And I guess, Jennifer, I turn this over to you.
Actually, I'm going to let Glenn Bertini ask a few questions.
Okay.
Hi, Glenn. Yeah, some great questions from Nikki and Steve and Gail and Tim and Charles and Sheila.
Oh,
We're
dear.
not going to get to them all.
Let's try it.
But let's get to a couple of them, and then we'll answer those that we don't get to by email or something later on.
Okay.
First question from Gail is, go ahead, Glenn.
I was just going to say, they should email the questions to you? Or they can email?
No, we've got the questions on my screen in front of me, so
Okay.
we'll take it from there.
Okay.
Yeah, Gail asked, these various studs, first of all, are they standardized between manufacturers?
The stud on the 600 amp T-bodies are determined by standard by IEEE 386. There are 2 of them that are standardized, and every manufacturer has to meet the dimensions. Again, the issue was if you have 15 and 35 or 25 and 35 kV class systems in your particular utility, and somehow those studs get mixed up, there's a problem. There is also the stud that's unique to one particular connector system, and that is not called out by standard. So that's one that currently falls through the cracks.
So in short, they're somewhat interchangeable, but not universally interchangeable.
Right. The ones that are called out in 386 are universally interchangeable. And by the way, something I did not mention, the next revision of IEEE 386 is going to change the dimensions for the 15 and 25 kV interface, so that if by chance someone uses the 35 kV stud, if they do get mixed up, that it will not bottom out. So that's going to happen in the next revision of IEEE 386. The old version of that interface affects very, very few. In fact, I believe only one utility anymore, so it won't be an issue.
Okay. For those that need to drop off because we're past our time, feel free to do so. We're going to stay on for maybe 5 more minutes for 2 or 3 more questions, and before we call it quits here. The next question from Charles is associated with the grease that's applied onto that interface of the separable connector. I think everybody that's been in the field and operated old elbows has seen this sort of white paste that's left. It doesn't look anything like the grease that was applied 20 or 30 years earlier. So first of all, where is that grease going? Why does it change? And if it is leaving, do we need to remove those interfaces periodically, clean them, and reinstall grease?
Okay. Years ago, and I'm going back over 25 years now, the original greases that were used back then are different than the ones that are used today. Back then, the revision of IEEE 386 did not have a performance criteria for the grease. That's the first issue. Once this whole problem with what we call sticking interfaces came about, a tremendous amount of work was done, and what we found was that those old greases just didn't work. When you mated the interface, it does migrate out, as I mentioned. There was a University of Connecticut study done several years ago. It's probably easy to get a copy of that study, but the pressure actually forces the grease out. Now, the thin greases that I mentioned, when someone uses a very thin grease, it migrates out very easily. The thicker greases, the ones that are supplied today, actually meet the performance criteria that is now in IEEE 386. And it's a pretty severe criteria. What we found is in most cases, the surface is just not, the entire surface is not coated with the grease. The white film that you're seeing there, what that is the liquid portion of the grease is migrating out, and what's left is what we call the filler, the silica. And that's what the white is that's left behind. And yeah, that is very difficult to separate those interfaces. You should still be able to get them off. One important thing you should do is every time the load break elbows or any of these connectors are separated, they should always be re-greased. Now, I only caution you on load break connectors. That's the most critical one, because how do you grease a live elbow? The way to do that is if a splicer is removing an elbow off a live bushing, he has to put that elbow somewhere. He can't just leave it floating in air. He is either going to put it onto a feed-through, a junction, a standoff, a grounding plug. The best way to do this is grease the mating part well before you put it onto the parking stand. This way, when you put the elbow on, it will now recoat the interface of the elbow.
Okay, and it's sort of a related question. What's the anticipated life of a modern accessory in decades? And do you expect the grease to remain there for that entire time?
The original connectors that were developed, I showed the 200 amp dead brake connector. That was actually developed in 1962. That was the first connector. The load brake line and the dead brake line and even that splice line came very, very quickly after that, in the late 60s, early 70s. All of those products that were originally developed were all manufactured with a sulfur-based curing system. Unfortunately, that particular curing system had a life expectancy, and it was the higher the voltage, the shorter the lifespan. And it related to the way the molecules, the actual polymer, is bonded. In the certainly by the late 90s, 1990s, all separable connector manufacturers manufactured their connectors with a peroxide-based insulation system. And in comparison studies, these were accelerated tests, and the peroxide-based materials just didn't fail. the sulfur-based materials would fail within weeks to months, and the peroxide-based materials went years and didn't fail. Now, if you look at the life expectancy of a sulfur-cured material, we do have some very specific data that shows a sulfur-based 600 amp elbow has a life expectancy of 15 to 20 years in a dry environment. Put it in a wet environment, it's even worse. So it's not unreasonable to see that a peroxide cured product will match the cable life expectancy. And those are predicted out at 40 years, so I certainly don't see any problems with those. As far as the life expectancy of the grease, I don't have an answer for that. I'm sorry I don't have any accelerated data out past a few years. So maybe someone else that's on the webinar may have some information that they could pass along.
Hopefully somebody does. Please send that to me in an email, and we'll pass it to everybody else. We're going to take the rest of the questions offline, and I'll turn it back over to Jennifer. Thanks, Glenn.
Thank you all.
So thanks to everyone for participating today. Please make sure that you complete the survey now that the webinar is finishing, and if you have any additional questions, please feel free to contact me. My email address is on the screen, although you probably already have it from your invitation. So again, thank you very much.